Today I'm going to talk about data hiding based on quantum state discrimination. And this is a joint work with my, it's not on. No, it's on. Yeah, this is a joint work with my postdoc, Dong Ha, who's sitting there. Okay. So yeah, this is the outline. First, we'll talk about bipartite quantum state discrimination and some possible constraints on the set of measurements, such as PPT measurement and ROCC measurement. Soon we'll see what this means. Then we'll talk about data hiding scheme based on quantum state discrimination. And we can also see how reliably the data can be hidden in an asymptotic way by using the concept of multi-fold ensemble and some task therein. Then we'll see some sufficient conditions for quantum data hiding. Actually, we'll provide two independent bounds for LOCC discrimination. And one is for constructing quantum data hiding using entangled state. And the other bound is for quantum data hiding with only separable states. Then we'll summarize. Yeah, now it's working. Okay. So as mentioned before, we mainly talk about bipartite quantum system. So the states here is a positive operator with unit trace acting on this bipartite Hilbert space. And also the measurement is a set of positive operators with this completeness acting on this bipartite Hilbert space. So in this workshop, I guess the concept of state discrimination has been mentioned several times. So let's briefly see. So there's a set of states, say from row 0 to row n-1. And one of the states will be prepared probabilistically. So in other words, row I, for each I, row I will be prepared with the probability eta I. Then the task of quantum state discrimination is to guess which state is prepared. Or in other words, to guess the index of the state. Okay? And for this situation, we'll use the term quantum state discrimination of an ensemble. Here, the ensemble consists of the states row i's with the corresponding probabilities. Okay. Maybe use this one. So of course, to get any information about the prepared state, we need to perform measurement. So we're going to use this set of measurement operators. And the decision rule here is like this. If M0 is detected, then we just guess the prepared state is row 0, no matter what the actual state is prepared. Okay? And also the probability of detecting Mj when row I is prepared is known to be the inner product of these two operators. It's called Bohn's rule. And the average success probability, when we use this, for this given ensemble epsilon, when we use this measurement M, then the average success probability is the expected probability that each row I is correctly guessed. And of course, as the probability, the success probability is always between 0 and 1. And we also know that the perfect discrimination is possible if and only if all the states here are orthogonal, mutually orthogonal to each other. And the minimum error discrimination is to maximize this average success probability over all possible measurement. And the maximum value is also known to be the guessing probability. And here G is for the guessing, but also G here means that there is no restriction on the use of measurement. We can use any arbitrary bipartite measurement. So now let's think about some possible constraints on the set of measurement. An operator is called PPT, positive. It is said to have positive partial transposition if it's still positive after partial transposition. Because it's a bipartite operator, we can take transpose partially on either of the subsystem. And if the resulting operator is still positive, then it's called PPT. And a PPT measurement is a measurement whose measurement operators are PPT. Okay? Then if we think about the maximum of all possible PPT measurement, maximum of the average success probability of all possible PPT measurement, then we'll denote that maximum value as the PPT of epsilon. Okay? Then you can think about further constraint on the measurement set. If you only think about LOCC measurement, which can be performed only by local operations and classical communications, then the maximum of average success probability of all possible LOCC measurement will be denoted by PL. Okay? Then we can easily see that these kind of trivial inequalities, because every LOCC measurement is known to be PPT measurement, and every PPT measurement is some special case of general measurement. So we have these trivial inequalities. And also, if we just guess the prepared state as the state with the largest probability, then it can be also done with LOCC operation. So PL is always bounded below the maximum of the preparation probability. Again, this one is bounded below by this the probability of random guessing. So we have all these kind of trivial inequalities. However, if any of these two are strict inequality, then it means that PL is strictly less than PG. That means LOCC measurement cannot achieve the global maximum. So that means there is some non-locality in this state discrimination. And we're going to use that non-locality to construct some data hiding scheme based on this state discrimination. Okay, so let's talk about quantum data hiding. So let me tell you what I mean here by data hiding. So let's consider the situation. There is a hider who's going to send this n-array data X to these two people, say Alice and Bob. But there is a condition that if just Alice and Bob alone, I mean, if they do not collaborate, they cannot obtain any information of the data. That's the condition. And the data can be recovered only if they collaborate. Okay? So in the sense that the data is hidden from each of Alice and Bob. And the only way to recover this data is to collaborate. Okay? So the term data hiding makes sense here. If we want to do this quantumly by using state discrimination in the situation, one way to do this is to use this state ensemble. Using this state ensemble, the hider will send one of the state. The hider first prepare one of the state from this ensemble and send to Alice and Bob. Because these are bipartite state ensemble, one part, he can send one part to Alice and the other part to Bob. Okay? And for data hiding, if they don't do any collaboration, in other words, if they just do LOCC measurement, then they cannot obtain any information. So it's the equivalent to say they can do no better than just random guessing. So that means the PR, which is the maximum of all possible LOCC measurement, must be 1 over n, just random guessing. However, if they can do collaboration, that means they can do any general measurement, joint measurement, they can perfectly discriminate what the prepared state is. So in the language of state discrimination, PG epsilon must be 1. Okay? So to construct this kind of quantum data hiding scheme, we need to find some state ensemble satisfying these two conditions. Okay? However, so first we can see that there must be some condition on this ensemble. So for this perfect discrimination, as I mentioned before, this state here these must be mutually orthogonal to each other so that they can have this perfect discrimination. Okay? And also, for this complete randomness, this probability distribution must be random. If we just this state ensemble just using just one time, okay? And on top of that, it's still a hard task to evaluate this optimization of all possible LOCC measurement. It's because the structure of LOCC measurement is very hard to characterize in a mathematical way, okay? So instead, we're gonna use this ensemble several times. Okay, so instead of just using single use of this ensemble, we'll prepare, or the hider prepare state several times from this ensemble, so that in the first round he prepares this row C1 and so forth. Then the state of the system after this iteration of preparation will be described as the tensor product of the states at each preparation. Okay, and each preparation is independent from each other, so the probability of preparing this product state, a tensor product state, is also just product of the probabilities of each round. Okay, so to indicate this tensor product state and this product probability, we'll use this vector notation for the index of the states. Okay. So this index means that in the first round, row C1 is prepared, and so forth. Okay? And we also define another quantity, which is called the modulo n weight, which is nothing but the modulo n weight of the index vector C, which is just the summation of all these entries in this vector in mod n addition. Okay? So it's clearly again in this Zn. This is one of the integers from 0 to n minus 1. Okay? So now we can think about this multifold ensemble, which is just nothing but just nth iteration of preparation. So to have this multifold ensemble, and for given this ensemble, we think about the situation of guessing the weight of the index vector of the state instead of discriminating which state is prepared. Okay, so it's an easier task than just discrimination of the actual state. Okay. Equivalently, we can also think this situation like this. For this L-fold ensemble, we just think about the states whose the weight of index vectors are all the same. Okay, we can just think about those states from here having the same weight of the index vectors. We can take the average with this normalization and the probability distribution, so that we can have this another state ensemble, which is the ensemble of average states, right? And the situation of guessing the weight of the index is equivalent to say that state discrimination of this ensemble of average states. Okay? Right, so the data hiding scheme based on quantum state discrimination is to use this task, guessing the weight of the index vector for a given prepared state. Okay? So the sufficient condition for the data hiding is that if they do not collaborate, they can do no better than just random guessing. That means the PL of this epsilon L must be random. But because I told you that we're going to do this asymptotically, this one tends to 1 over n when L tends to the infinity. So in an asymptotic sense, it can be randomized. And of course, PG of epsilon must be 1, because if they collaborate, they can do the perfect guessing of the weight of the index. Okay? And also, we can note that if the original state ensemble epsilon is orthogonal state ensemble, then everything here is orthogonal. Everything here becomes orthogonal, because if this one are orthogonal to each other, then you can easily say that this one is also orthogonal for each index. So if you take some average of some states there with same index weight of the index, they are also orthogonal to each other. So the orthogonality of this epsilon implies orthogonality of everything, right? So the detailed scheme will be like this. The first hider, first prepare state rho C from this epsilon, and he just repeat this, say roughly L times, okay? So that the state of the system will be like this, okay? So equivalently, we can also say that the Heide first prepare a state from this Alford ensemble, then send this to Alice and Bob. So there are actually some technical difference. If Alice and Bob has quantum memory, then when they receive the state, they can just store this state to the memory, so that in the end they can have this state. However, if Alice and Bob do not have quantum memory, then they need to perform measurement as soon as the state is received. Okay, so in that case, there can be more restriction on the measurement that they can use, right? But anyway, we're gonna do the analysis for this situation. Okay, and the hider want to hide is X, this n-ray data. And Y here is defined as the weight of the index of the prepared state, weight of C. And the hider will announce the summation of this X and Y. Okay? So to Alice and Bob. So once Z is known to Alice and Bob, to recover X, they need to know what Y is, which is the weight of the index. Right? But as mentioned before, if this condition is satisfied, then they need to collaborate to recover the data Y. Okay? That's the idea of data hiding, or that's the condition for this quantum data hiding. So now we need to think about in which case this condition will be satisfied. Excuse me. So the first thing, we'll think about a bound of PR, which is called QG of epsilon, which is defined like this. So for given state ensemble epsilon, this QG is defined as the maximum average of the inner product of the this measurement operator and the partial transposition of rho I. Okay. And a couple of years ago, what we could show is that this is an upper bound of PPT, the maximum of all possible PPT measurement. Okay, you can actually easily see why this one is an upper bound, but yeah, I don't think I have enough time. So anyway, so this one is an upper bound for PPT. So instead of randomizing this PR, we can randomize this quantity so that everything here will be equal to each other. Right, and another inequality we could obtain about this QG is that for any ensemble epsilon, if we think about QZ of this epsilon L, which is the task to guessing the index, the weight of the index, this is bounded above by this quantity. This is true for any arbitrary state ensemble epsilon. So to randomize this one, we need to think about the condition where this one vanishes. Okay, so if the term inside this power is strictly less than 1, then it will vanish as L increases. So then we can randomize this quantity, right? So yeah, so that's one condition. So for any quantum state ensemble, if we have this condition, QG of epsilon is less than 2 over n, then this PL of epsilon L will tend to 1 over n as n increases. So yeah, that's the condition. For every bipartite orthogonal quantum state, of course, we need to do a perfect discrimination when Alice and Bob do collaboration. So it must be orthogonal quantum state ensemble. And if it satisfies this inequality, strict inequality, then this one can be used to construct quantum data hiding scheme. And we can also find some example easily. So for the case when n is 2, we can think about any NPT quantum state, which means it has some negative eigenvalues after partial transposition. then it implies that the trace norm of this sigma pt is strictly larger than 1. By using this, we can define these two quantum states with these probabilities, and they are orthogonal to each other because of the construction. If you multiply these two, this is nothing but the zero operator, so they are orthogonal. And we can also show that this ensemble has this condition. I mean, the inequality. The QG is strictly less than 1, which is the case of which is equal to 2 over n when n is 2. So that means PL of epsilon L tends to so in this case, this is 1 over 2, right? Yeah, this is typo. So anyway, so we can easily find some example. This is for the case when the data is binary data. And we can also think about data which is more than binary. So yeah. So for any n, which is a power of 2, we can think about this states, which is known to be the symmetric and anti-symmetric Bernoulli state. And by using this repeatedly, we can construct this state rho I with some appropriate probabilities. Then we can show that this one satisfies the condition that QG of epsilon L is less than 2 over n, which is the condition before. Yeah, the condition before. So, and in fact, if n is not exactly equal to 2 over m, then we can use sum of the state here to do quantum data hiding. So this is actually true for any arbitrary integer n. And this is a graph that how rapidly the PL of epsilon L tends to the random guessing. So for the case when the number of states are 3, 6, or 9, so after a couple of iterations, the PL, actually this is the upper bound of PL, the graph means the upper bound of PL, rapidly tends to the random guessing. Okay, so this is sufficient, this scheme is sufficient enough. Sorry, this scheme is good enough. We don't really need to do many iterations. We can also generalize this to the situation of a multiplayer data hiding scheme by using multi-party quantum state discrimination, but I don't think I have enough time. So if you have any interest, then please have a look at this manuscript on the archive. Right, so far we talked about the quantity QG to randomize this PR. However, if the state ensemble consists of orthogonal PPT states, then we can easily see that this QG is always 1. Okay? Because if the state here, rho I, is PPT, then after the partial transposition, it's still a state. And the orthogonality is not changed under partial transposition. So QG is always 1. So that means, so if we want to use this QG to randomize this PR, then there must be some entangled state in this ensemble. Okay? With only separable state, every separable state is PPT, so that means QG is always 1. So a natural question we can ask here is whether we can construct any quantum data hiding using only separable states. Or equivalently, whether entanglement is necessary for quantum data hiding. And the answer is not. Quite recently, we could find some separable state ensemble which can be used for this quantum data hiding. So entanglement is not necessary from our result, for quantum data hiding from our result. To randomize this P of epsilon, we use the notion of lambda epsilon. So let's think about this epsilon, which has these two states. two-state ensemble, the lambda epsilon is defined as the difference of these two with this probability. Okay? Of course, the choice of 0 or 1 is dummy. You can also switch those two. It doesn't matter. So anyway, and let's think about the condition that this lambda epsilon is invariant on the partial transposition. That means this is still the same after partial transposition. And this is actually equivalent to say that there exists a Hermitian operator H which decomposes this lambda epsilon in this way, H plus HPT. Okay? You can easily see why these two are equivalent to each other, because if this one is true, then you can use the half of lambda epsilon as H here. And if lambda epsilon has this decomposition, it's clearly invariant on the partial transposition. Okay, then what we could show here is that for the two-state ensemble satisfying this property, then the PPPT of epsilon is bounded above by the trace norm of this H together with this half. One thing we can note here is that, of course, if this lambda epsilon is PT invariant, we can use this half of lambda epsilon as H, but we note that this choice of H is not unique. That means if lambda epsilon satisfies this property, then there can be several H which decompose this lambda epsilon. And for any such H, if we think about its trace norm, it will give an upper bound of PPPT, right? And moreover, if we think about the minimum among such H, which decompose this lambda epsilon, then it will give the actual value of PPPT of epsilon. Okay? And what we could show more is that if we think about PPT of epsilon L, if you remember, this epsilon L means the task of guessing the index of the prepared weight of the index of the prepared state. Then for the case when this state ensemble satisfying this property, then this PPPT epsilon L is monotone decreasing with respect to this L, the number of iterations of preparation. And because we know that this PPPT is always bounded below by the half, and with respect to this L, this is a decreasing, monotone decreasing sequence, real sequence. So now we know that this is a convergent sequence. Okay? So any subsequence that has limit as a half, then we know that this one, the limit of this one is a half. That's the method we're going to use to bound this PL of epsilon L. So for the two-state ensemble having this property, invariant on the partial transposition, and if the trace norm, if there exists a Hermitian operator H, whose trace norm is less than or equal to this quantity, then we could show that, so this is the subsequence of PPPT epsilon L, because we only think about the power of 3 here, then it's bounded above by this quantity. So we use this, this one seems a bit arbitrary, but so we use this one to show this inequality. Maybe you can find some better inequality, but anyway, so we could show this one, and also this one also implies that the term inside this power is less than or equal to 1. Okay, so it means if this trace norm of H is strictly less than this quantity, that means this one converges to a half. The subsequence converges to half. That means the original sequence also converges to half. So by using this, we could find a separable state ensemble which satisfies the condition. So that means the state R here is consists of this rho I, and rho I is constructed by using this separable states, using the iterative preparation of these separable states. So everything here is separable, and for this state, it satisfies the condition here mentioned before. So we can use this separable state to construct quantum data hiding. Okay. So this is the graph, how rapidly that PR converts to the random guessing. Okay, so it's almost at the time. So let's summarize. So in this talk, we have provided some quantum data hiding scheme based on bipartite quantum state discrimination. We have two conditions. One can be used for data hiding using entangled state ensemble. And we also provide some separable state which can be used to quantum data hiding. So we can say that entanglement is not necessary for data hiding. And possible future what we can think about here is that first we define the quantity QG and we use this one to bound PR. So we need to find some operational meaning of this with respect to this data hiding. But still, this is a sufficient condition, but not necessary. We want to find some operational meaning of this QG. And and finally, so we are wondering whether or not, which one is the necessary and sufficient condition for quantum data hiding. I mean, what kind of non-locality, non-local correlation is needed and also sufficient. Okay, so I guess that's all. Thank you.
So we have time for one or two quick questions.
Thank you for the talk. I have two questions. The first one is when you explain the hiding situation, Hyder, Alice, Bob have to consider Z equals to X plus 1. So I don't know why, I don't understand why they have to consider it. It looks a little bit artificial. And the second question is, can I conclude that even if they have optimal measurements but they are considering L-fold ensemble, but it converges to the random guessing probability even if they have optimal one.
Yeah, so for the second question, that's why we show the reliability of data hiding in an asymptotic way. So it's not like one-shot, randomness. And also, I've shown the graph that the convergence to the random guessing is quite rapid. For the first case, like 3 or 4 iterations, you can have enough randomness. That's answer to the second question. And the first question is, was it about this?
Yes.
So your question is why Alice and Bob consider... Sorry, could you repeat the first question?
Yes, so why they have to consider Z?
Oh yeah, so after the preparation of the state, what Hyder will do is to make the addition of this X and Z. X is the actual data he wants to hide, and but instead of just sending X, he will send Z, which is the addition of X and Z. So X is the actual data of that Hyder wants to hide. And so Y is a kind of key to encode this X to be hidden. So once Z is known, you need to know what Y is to decode this X.
Yes, so even if...
Oh yeah, okay, so one more. So the choice of Y is just random. So Hyder cannot control the choice of Y. I mean, which is the weight of the index vector. But the data can be your choice, the Hyder's choice.
Yes, so Hyder hide X, but Alice and Bob have to guess after the state discrimination, they can guess what X is. So there already some randomness. They have to guess. So
in order to know X, they need to know Z in advance, which is announced by Hyder. Yeah.
So thank you for the discussion. Because of time limitation, let's thank the Professor Kim again.